Okay, the first presentation, as I said, by myself and Mr. Baranyai, is about integration of grid measurement data on smart meters for improving observability of distribution grids, medium and low voltage grids, and we present some results for case study of distribution grid in city of Geneva. So we have, it's a joint presentation. In the first part, Mr. Baranyai in a few seconds will present the structure of SEG plus their mission and their challenges with respect to energy transition. And then for the second part, I will present some methodologies developed and results we achieved mostly within the frame of the digitalization program of SCCER-FURIES. Now move to the next slide, and I ask Mr. Baranyai to take the floor.
Yes, hello everybody. You listen to me, Mokhtar?
Yes, we can hear you very well.
Right, hello everybody. My name is Michael Baranyai. I'm an electrical engineer, and then I manage the network electricity in Geneva. As those first things, I'm going to introduce my society. Although SIG provides essential daily services based on its know-how in the management of energy, of water, optical fiber, and waste processing network. We are serving 228,000 customers, and we are a quite big society because we employ more like 1,600 people. And the high proportion of is in engineering is the blue part. Next, please. Thanks. You know, we are in a changing context, decentralized production storage perspectives, artificial intelligence, big data, industry 4.0, cloud, etc. Changes in customer behavior, willingness to reduce environmental impact, phasing out of nuclear and fossil energy, smart, sustainable and connected neighborhoods, and evolution of work, culture and professions. Next, please. Although with this changing context, we must keep our mission for the distribution network. So the mission is connecting building to the different fluids like gas, water, electricity, and extending the network necessary for the economic development of the Canton de Genève. Guaranteed high quality supply by maintaining our numerous installations, supporting our customer 24 hours a day, managing more than 300,000 metering installation, integrating the development of new technology, enhancing multi-fleet synergies. In the right side, you can see a small map. It's the middle voltage network. Also, the characteristic of the middle voltage network is we have about 1,500 substations. When we convert the middle voltage to the low voltage and alimented the different customers, and inside the substation we have 2,500 transformers, 1,000 kilometers of cable, and the proportion of the underground cable is for the middle voltage 90%. Next, please. And the development of SIG solar energy aims to double solar production in the canton by 2025. And also for the goal in the next 5 years, we are 150 megawatts in power photovoltaic productions. Next, please. Although the recent increase of uncontrolled renewable production connected to the distribution network raised the need for better network monitoring and control solution. Now, before we have a small map of the middle voltage, and now you can see a small map of the low voltage network. And the characteristic that inside the substation, we have more than 8,000 feeders to alimент the network, low voltage network. And inside the low voltage network, we have also some couplage, 2,500 different couplage. The characteristic is 4,000 kilometers the cable. It's the same like the middle voltage network. We have 90% of underground cable. Although the medium voltage and the low voltage distribution networks are very large in terms of number of lines, nodes, and we are looking for monitoring and supervision systems that require a limited number of affordable grid measurement device by also using the value of the smart meter, and we are working with the HES-SO VD for that. Thank you for listening to me, and it's your turn, Mokhtar.
Thank you, Michael. So in the rest of this presentation, I will present you the methodology and results we basically developed to achieve this observability at medium and low voltage network of City of Geneva. So the idea of the first project, Grid Data Synergy, was to use these two sources of data. So we have smart meters data coming every day, but we have a, let's say, batch set of data which are not available in real time. We also have data from some measurement devices that are connected at the grid side, and we wanted to do some integration and to take advantage of the synergies of having these two sources of data. The challenge is that we have a lot of, we have a big network in terms of number of lines and nodes, and the data of smart meters are also not available in real time. So what we first developed was a data integration platform. So using database technologies to kind of automatically take the information from two sources of data. And then we developed a distribution system state estimation algorithm that provide the observability through state estimation. But this state estimation requires not just measurements from grid measurement devices, but also requires pseudo measurements from loads at the customer side. So we developed the 3 different methods for forecasting the loads or the pseudo measurements based on the available information from smart meters. So the partners of the projects are our school, SIG, and Depsys as the provider of grid measurement devices. So for DSSE, for state estimation, what we proposed is a DSSE based on dist flow model. Why dist flow? Because within this available measurement devices, we do have access to the voltage magnitude, measurements of voltage magnitudes, and power flow measurements, but we do not have access to we do not have access to the voltage angles with enough accuracy. The problem is that in the low voltage networks, the lines are quite short, so the phase angle difference between two neighboring lines can easily reach the accuracy level of devices. So we developed the DSSE algorithm based on dist flow model, which requires voltage magnitudes and power flow measurements. We enhanced the state of the art here by adding considering the model of line capacitance, because as Michael said, most of the lines are underground cables where the capacitance of the cables are not negligible. Here is some hypotheses we have made to formulate our state estimation. So we assume that we have a slack bus on the high voltage to medium voltage transformer level. Then we have a set of devices connected at the LV side of the network and of a few nodes, and all the loads are basically forecasted in an intraday basis to generate the so-called pseudo measurements. The measurement devices are providing voltage magnitudes and active and reactive power measurements, and the key assumption here is that the parameters of transformers and cables are known. So the first case study is this one, where we have 52 nodes. We have in this district, actually, we have 58 smart meters and still 31 conventional meters. So something like 65% of the buildings are equipped with smart meters. We have installed 2 measurement devices at the LV side of the medium voltage transformer, and here just at the beginning of these LV feeders. In terms of data, we used the 79 days of available data of both smart meters and measurement devices, and we used the last 8 days to test the performance of the developed algorithm. We have defined 4 cases. In the first case, we use measurement device. We do not use measurement devices data here. We only use smart meters data to do the state estimation. And then in the following 3 cases, we have developed 3 different methods for generating pseudo measurements, which are the power injections at each node or power consumption at each node, and based on 3 different methods, which we will see in the next slide. So what are these methods? The first one is used as baseline. So it's a classic seasonal ARIMA method, in which we use the historical data of the past 70 days to generate, to optimize the model, and then based on that to do the forecast. And then here we only use smart meters data. In the second and third methods, we use random forest as a kind of machine learning approach. And the difference between method B and C is that in B, we only use smart meters data, and in C, we use both smart meters and the measurement devices. Well, in terms of results, here in left, you see the results of active and reactive power forecast. So in blue, we have the actual power in the last 8 days, and in orange, the forecasted one for the data of all the smart meters in this feeder. And the thing is that the level of error is quite acceptable in the range of 8 to 9%. But if we move to if you run the forecast for each node separately, so the average error of nodal forecast can reach is somewhere between 30 to 40%. Well, using the difference is that, of course, using the novel approaches, machine learning based approaches, we obtain better results in method B and C for both active and reactive power forecast. And the difference between method B and C, using additional data from measurement devices, in this case, did not help considerably. The reason is that, it's improved by like 1% the error of forecast of active power. The reason for this is that if I move back to the previous slide, so we want to forecast for each node the load. And if you have a measurement devices that is installed upstream the network here, basically it does not, data does not have the detailed data of the disaggregated data of each node. So the help that it can bring in real time is not considered. Still, it is helpful because compared to the smart meters data, we have more recent data. So we have the data of the past 10 minutes, whereas in the case of smart meters, we only have the data of the past 24 hours. So this is the results of intraday nodal load forecast. And then we use this data to feed our state estimation model. There, we can see some results. First of all, in left, we see the error of voltage estimation. In first case, we do not use the measurement devices, and the error of voltage state estimation is, you can see in average, is somewhere close to 3 or 3.5%. And by installing just one device in the 3 cases, so somehow independent of the approach that we use for intraday nodal load forecast, we reduce the error of voltage estimation. But in terms of error in current state estimation, it's a bit more complicated, because with the measurement devices, again, connected at the top of the network, we cannot do, let's say, a lot of improvement. So here in these 3 graphs, we see how we improved with respect to case 1, which is the baseline in which we do not use the measurement devices, how we improve the error of a state estimation for in the whole network. So in the color code shows for each node the improvement percentage of voltage estimation, and for each line the improvement in percentage of current state estimation. Well, in the first case, when we do use ARIMA and we do not use the measurement devices for the forecasting, we can see that still some line current estimation is not good. We can see also in the average numbers. If we move with case 3 and case 4, in which we use random forest approach for the forecast, so of course we have a better forecast of pseudo measurement, so we expect to have better or smaller error of state estimation, and we can see in these 2 figures, and then the difference between the 2 figures are marginal. It's about better forecast in case of having measurement devices, also better state estimation for currents in few lines, for instance here in line 28, or some few others down there. So with this, actually, I wanted to conclude our results. The first important thing is that the overall load forecast can be between 4 to 9%, and by overall I mean at the level of the MV to LV transformer. But if we move deeper into the LV node forecast, the nodal load forecast can reach up to, the error can reach up to 30 to 40%. And within the methods, random forest clearly outperform the baseline, which is seasonal ARIMA. Adding measurement devices can improve the state estimation error and can improve the nodal load forecast, but the level of improvement is a function basically of the number of devices that we install. And with this, and our, let's say, first estimation is that it improves around 1% in average per additional measurement devices. So to further actually investigate this, in the, let's say, next activity, we wanted to see, okay, we have now a method for state estimation that provides some level of observability, but how many devices we do need to install in the network and where to install it in order to achieve a certain level of observability. So the approach is to develop a greedy placement optimization, and the input of the optimization problem is the error of state estimation for different cases. So here is a summary of the method. We have defined 20,000 initial scenarios with respect to the error of load forecast, with respect also to the error of measurement devices for voltage and current inaccuracy. Then we define a cost function, which is for every node, which is the difference between the desired observability level, which is defined based on the variance of state estimation errors for different scenarios, the desired one and the one that is compute. And then the approach, the greedy approach is an iterative approach in where we start to install a set of devices. And then for any additional devices, we look at the node that could minimize actually this cost function to be selected as the candidate for installing the measurement devices. So with this approach, we tested the approach on another distribution network in Geneva with 85 nodes, where 10 nodes are at medium voltage here, and then we have the branches down there at the LV network, including 75 nodes. So this is the loading of the network in terms of so the color code is for each line is the power flow of the line, and for each node is the power consumption of the node. The first thing that we have done is, okay, without having any measurement devices, what is the expected error of state estimation? And then in this figure in right, we can see that, well, up there, and we know that the voltage of slack bus, of course. So up there, when we are close to the slack bus, the level of error is quite acceptable. Where down there in the LV network, we are in the red regions. So the desired values of state estimation error is 0.3% for voltage estimation and 5% for power flow or current estimations, which cannot be achieved using only smart meters data. So we run the optimization algorithm for two cases. The first case, when we only look at the voltage to improve the observability of voltage estimation, and we respect this constraint that voltage estimation should remain with lower than 0.3%. With this, we need, for instance, here 5 devices, but still, with these 5 devices, we cannot achieve the required error for current estimation. We see some lines here which are in orange and red, which means that we have high error of current estimation. Then, to respect the current estimation, here in this figure, we see that we need to have 3 more devices. So to respect these desired values of estimation error, at the end of the day, we need to install, for instance, 8 devices in the 85 nodes network. So I conclude the presentation actually with the very last result on how the number of measurement devices that we need is changing as a function of the error of pseudo measurements, the error of intraday nodal load forecast. So they have 2 cases of 20% or 50%, and in case of higher load forecast, we need more devices to install, and also with different loading scenario of the whole network. But the key trend is that, of course, the higher the desired observability, the higher the number of measurement devices that we need to install in the network. So with this, I'm done with the presentation. Thank you for your attention. And if you have further question, you can raise your hand or write in the chat, or you can refer to the few publications we had and send us an email as well.